Hello once again. So we're going to discuss, okay, so on this presentation, so higher order differential equations. So by the way, I hope you are all still doing fine. We are done with first order differential equations, so the different methods on how to solve it, so together with its application. So this time around, so we will proceed with higher order differential equations. If we could still recall that whenever we're talking about the order of the differential equation, so that corresponds to the highest derivative on the given differential equation. Okay, so as long as the highest derivative starts from 2 and above, or the order of the differential equation is order 2 and above, then that is considered as higher order differential equation. So we can see here some examples of higher order differential equation. So one in the prime notation and the other is using the Leibniz notation. So we have a second order differential equation, y double prime plus 2y prime minus 1 is equals to 0. So that is a higher order differential equation. So similarly, so using the Leibniz notation, so we have the third derivative of y with respect to x plus the first derivative of y with respect to x is equals to sine of x. Then that is a third order differential equation. So the differential equations are, or these two examples of differential equations are collectively known as higher order differential equations. And there are different ways on how to find the solution. We're not specific on the order. As long as it is considered as a higher order differential equation, then we can solve it using the higher or the methods for higher order differential equations, as long as we are able to classify properly so what kind of higher order differential equation it is, because there are two types of there are two general type of higher order differential equation. So one is homogeneous equation and the other is non-homogeneous equation. So depending on the classification of the higher order differential equation, so it will dictate, okay, so what kind of method are we going to use. Okay, so for homogeneous equation, so we will be using the method for homogeneous equation, in this case the homogeneous linear equation with constant coefficient. So our discussion will be limited to those type of higher order differential equation. And then for non-homogeneous equation, so there are two methods that we can choose to. So one would be the undetermined coefficient, the other is the variation of parameters. Although there's no as long as a given differential equation can be solved using undetermined coefficient, it also follows that we can use variation of parameters when solving non-homogeneous equation. So to start with, so let's try to define first, how do we differentiate a homogeneous equation from non-homogeneous equation. So following its definition, a linear nth order differential equation of the given form of a sub n of x, so multiplied it with the nth derivative of y with respect to x up to a sub 0 of x multiplied with y is equals to 0. So that given form is said to be homogeneous. However, if the same equation, and then this time around, so we will be equating it to g of x, wherein g of x is not identically 0, then that is considered to be non-homogeneous. So as you can see on the given form of homogeneous and non-homogeneous, so they are the same. So the only difference is the g of x. Okay, so the only difference here is just this g of x. Although this one has a g of x as well, but then the g of x for homogeneous equation is equal to 0. But then if we have a function, so other than 0, or an x function other than 0, so where the equation is equated into, then that is considered as a non-homogeneous equation. So that's the only thing that we are looking at the differential equation, so whether to classify it as homogeneous or non-homogeneous. So going back on our example here, So as you can see, so we have the second derivative, the first derivative, and then it's just a constant minus 1. But actually this one is the same as y double prime, so plus 2y prime is equals to 1. So we have the derivatives of y, and then in here our g of x would be considered as 1. So therefore this is a non-homogeneous equation. So similarly, so we have the derivatives of y, and then our g of x, so would correspond to sine of x. So then we have a sine of x as our g of x, then that is considered as a non-homogeneous equation as well. But then if I would have, for example, y double prime plus 2y prime plus y is equals to 0. And as you can see here, so we just have the dependent variable y, so together with its derivative as the parameters involved on the given equation, then this is considered as a homogeneous equation. Okay, so this is a homogeneous equation. So since our g of x here would correspond to 0. So as long as our g of x is not equal to 0, then that make it non-homogeneous. But if g of x is equal to 0, then that makes it as a homogeneous equation. So that's how we differentiate homogeneous from non-homogeneous. So now, so let's try to talk about the solution of higher order differential equation. So how do we verify so whether a solution is a solution of the differential equation or not? So it's the same thing as what we did for first order differential equation. So the only difference is for first order differential equation, so since the order is just 1, so therefore we only derive the solution once only as for the first derivative. In higher order differential equation, since the lowest order that we can get would be a second order, so just like in this case, so we have ay double prime plus by prime plus cy is equals to 0. So that's an order 2 differential equation. So therefore, so to verify so whether the given equation is or the given solution is a solution or not, then we derive it 2 times. So how do we verify so whether this is a solution or not? So actually, ay double prime plus by prime plus cy is equals to 0. So that makes it as a solution. As long as once we change it, or once we substituted the y prime and y double prime, and then it yielded to 0, then that makes it a solution of the differential equation. Example, we have a solution. The solution is a function of x, so which is g of x. So I just need to find what is y prime, so which is g prime of x. Y double prime, so which is equals to g double prime of x. Then substituting, so a, our y double prime is g double prime of x. Then plus b, our y prime is g prime of x. And then plus c, our y is g of x, which is equal to 0. And as you can see here, the only difference is one is using the y prime notation. So this time, I'm just using g of x. Okay, so a function of x. But then that would still be equal to 0. Then 0 is equals to 0. So then that makes the solution y is equals to g of x a solution of the differential equation. Okay, so as long as ay double prime plus by prime plus cy is equals to 0, then that makes it a solution of the differential equation. So what if we are given a function and then we multiplied any constant coefficient to the function? So will it still be a solution of the differential equation? So let's say, for example, if I would have y is equals to e raised to x. So let's say y e raised to x is a solution of the differential equation. Does it follow that y is equals 3 e raised to x is a solution as well of the differential equation? Is y is equals to negative e raised to x a solution of the differential equation? So let's try to find out here. So let's say I would have y, so which is equal to kg of x. So wherein k is constant. So y prime then so would be k g prime of x. Then y double prime so will be k g double prime of x. Then I'm going to substitute it here. So so y double prime is k g double prime of x. Then plus b, y prime is k g prime of x. Then plus c, y is k g of x is equals to 0. And x can be factored out. So giving us a g double prime of x plus b g prime of x, then plus c g of x is equals to 0. And we can say that this term is actually equal to 0. So that's making k times 0 is equals to 0 and 0 is equals to 0. Therefore, that makes it a solution of a higher order differential equation. Okay? So, for a given function, and then that function is just multiplied with, or it just have a, or it just has a constant coefficient. Okay, so if the solution of a differential equation so would just be multiplied with a constant coefficient, then it is still a solution of the differential equation. Okay. Next, so we have the superposition principle. In first order differential equation, if you had noticed, we only have a single solution. Okay? So we only have a single solution. So for first order differential equation. But for higher order differential equations, the order of the differential equation will correspond to the number of solutions of a differential equation. For example, we have a second order differential equation. The number of solutions there would be 2. And then for a third order, there are 3 solutions. For a fourth order, there are 4 solutions, and so on and so forth. Okay, so meaning the number of solutions of the differential equation corresponds to the order of the differential equation. But then, even though there are a lot of solutions, okay, so depending on the order of the differential equation, so there's only, or we could express them into a single general solution. Okay, so into a single general solution by using the superposition principle. So that is, let's say for example, we have let y sub 1, y sub 2 up to y sub k, so b solutions of the homogeneous nth order differential equation on an interval I. Then the linear combination. Okay, so the linear combination, so following the superposition principle, so y is equals to, we are just going to attach an arbitrary constant, the first arbitrary constant to the first solution. So just like this one, so c1 y1 of x. And then for the second solution, we attach the second arbitrary constant up to the kth arbitrary constant, so for the kth solution. So the linear combination, okay, the linear combination of all the solutions of the differential equation, so can then be classified as the general solution, or can then be put together, okay, so using the superposition principle, and collectively known as the general solution of the higher order differential equation. Okay, so let's try to prove. As if, for example, we have a second order differential equations, and as I have said, so there are 2 solutions. Okay, so since this is a second order differential equation, so similar to this, I have y sub 1, so which is the first solution, and that is a g function of x, and then y sub 2 as an h function of x. So therefore, y sub 1 prime then, so would be g prime of x, and y sub 2 prime, or double prime, or y sub 1 double prime would then be equal to g double prime of x. And then for the y2 prime, so would be equal to h prime of x, and then y2 double prime is equals to h prime of x. And then um, the linear combination, or sorry, uh, so let's say we have y sub 1 is equals to g of x and y sub 2 is equals to h of x. So which are the two solutions? Okay, so which are the two solutions of the given differential equation, or a second order differential equation? Then, so we can, using the superposition theorem, so we can go with the linear combination of the solution, so forming our general solution, so to be y is equals to attaching the arbitrary constant, the first arbitrary constant, to g of x, and then the linear combination plus c sub 2 h of x. Okay, so that will then correspond to the general solution of the differential equation, which is the linear combination of the two solutions of a second order differential equation. And then, so we find the first derivative, so as c1, so g prime of x, and then plus c2, so g prime or h prime of x, and y double prime, so will be c1 g double prime of x, and then plus c2 h double prime of x. Then we substitute it. Okay, so with the equation, so a then, so y double prime will be c1 g double prime of x plus c2 h double prime of x. Then plus b, our y prime is c1 g prime of x plus c2 h prime of x. Then plus c, our y is c1 g of x plus c2 h of x is equals to 0. Distributing a there, so that would, or combining all the g of x. Okay, so I'll start with this one. Okay, so everything that involves the g of x, so that would give us, I can factor out c1. Okay, so z1, so multiplied it with a g double prime of x, then plus b g prime of x, and then plus c g of x. And similarly, so we can do that one. So for h of x, so for h of x, so we could factor out c sub 2. Then I'll have a h double prime of x plus b h of x, or h prime of x, and then plus c h of x is equals to 0. And again, this is 0. This is 0 as well. So c1 times 0 plus c2 times 0 is equals to 0. So therefore, 0 is equals to 0. So thus, we can say that if y sub 1 is a solution of a differential equation and y sub 2 is another solution of the differential equation, then the linear combination of the two solutions, so using the superposition principle, the linear combination of the two solutions is still a solution of the differential equation. Okay? So in expressing, though we in finding the solution of the differential equation, so we're still going to find the number of we're still going to find the number of solutions of the differential equation if there are, or if that would be a second order, so we find the two solutions. If that would be a third order, we find the three solutions. But then in expressing our final answer, we usually express them in a general form. So using the linear combination of all the solutions, so forming the general solution of the differential equation. Okay, so that is for the superposition principle. So another thing that we need to cover would be the linear dependence and independence of the solutions. In a given differential equation, just so happens that the solutions, okay, of a differential equation are said to be linearly independent with each other. Okay, so all the solutions of a single differential equations are linearly independent with each other. If the two solutions or if the solutions are linearly dependent, then those are not a solution of a differential equation. Because for a given differential equation, so one of the characteristic of the solutions would be their linear independence with each other. Okay. So how do we define linear dependence and independence? So let's say we are given a set of function f1 of x, f2 of x, and up to fn of x. In this case, that would correspond to the solution of the equation. f1 of x is the first solution, f2 of x is the second solution, and fn of x is the nth solution. So those solutions or those functions are said to be linearly dependent on the given interval I if there exists constants c sub 1, c sub 2, or up to c sub n, not all zero. So such that the linear combination, okay, of the solutions together with the arbitrary constant. So if we could think for a value of c sub 1, c sub 2, and c sub n, that once we multiplied it with all those functions, and then it will lead to a value which is equal to 0. But then there's an exemption. C1, C sub 2, and C sub n should not all be zeros. Possible that, let's say, if this is a third order, there are two non-zeros and one zero. Or it's possible that two zeros and one non-zero. But not all of the arbitrary constant to be equal to 0. So that's how we make it as a linearly dependent. So if we can think of any combination of arbitrary constant not all equal to 0, that would make the equation, or that would make all the function or the linear combination of all the functions so to be equal to 0, that makes it linearly dependent. Because if we cannot find, okay, so a combination for those arbitrary constant so that would make it equal to 0, then that makes it linearly independent. Okay, so if the set of function is not linearly dependent on the interval, then that is said to be linearly independent. Okay, so to better understand this one, okay, so the only rule here is we're just going to think for the values of c sub 1, c sub 2, up to c sub n. But then, it is not possible that c sub 1, c sub 2, and c sub n should all be equal to 0. Okay? Possible that 1, okay, so only 1 would be non-zero. That would be okay. But it's not possible that all of the arbitrary constants should be equal to 0. So if we can think of the combination of all the arbitrary constant and it will make it 0, then that makes it linearly dependent. Otherwise, that would make it linearly independent. Okay, for example, determine whether the given set of function is linearly dependent on the interval I. So we have the first function as x, second is x sub 2, the third is 4x minus 3x squared. So let's try to do the linear combination of these. So I'm going to attach the first arbitrary constant to the first solution, or the first function, which is x, and then plus c sub 2, x squared, and then plus c sub 3, 4x minus 3x squared should be equal to 0. So this time, so we need to think of the values of c sub 1, c sub 2, and c sub 3. So that once I substituted those values to those arbitrary constant, and then it yielded to 0, then that makes it linearly dependent. Okay, so in here, so we just look at similar terms. So this is x, this is 4x. So x is multiplied with the first arbitrary constant, and then 4x is multiplied with the third arbitrary constant. So let's say I'm going to assume that c sub 3 so would just be equal to 1. So if I would have c sub 3 which is equals to 1 multiplied with 4x, that is 4x. So to make this one equal to 0, so I should subtract 4x as well. Okay, so 4x minus 4x would be 0. However, what I have here is x, okay, multiplied it with c1. So thus, if I can make this one as negative 4, okay, so that would cancel out the 4x. Okay, so negative 4 times x would be negative 4x, and then c3 is 1, so 1 times 4x is positive 4x. That makes it 0. So similarly, so for c sub 3, so multiply it with negative 3x squared, so that would make it negative 3x squared. So to zero that out, I should have a positive 3x squared. But then here, so I have x squared, so therefore I could make this one c sub 2 to be equal to 3. So once I substituted that one, so c sub 1 is negative 4 times x plus c sub 2 is 3 x squared. C sub 3 is 1, so therefore that would just be 4x minus 3x squared is equals to 0. So negative 4x plus 4x is 0. 3x squared minus 3x squared is 0. So therefore, so since that makes it equal to 0, okay, so then that since that makes it equal to 0, then so I could remove this one. Okay, so then this makes the combination so linearly dependent with each other. So that makes it linearly dependent. So in short, what does that mean? So that means that those three solutions are not a solution of the same differential equation. So those three solutions or those three functions cannot be a solution of the same differential equation because the three are linearly dependent with each other. So they are linearly dependent because we were able to think for C1, C2, and C3, all of them are non-zeros. Okay? So there is a combination of arbitrary constant values, so wherein all of them are not zero, then that makes it linearly dependent. The thing here is, actually there is no specific method on how to do this. We just need to think. Okay, so for the values of C sub 1, C sub 2, and C sub 3, so to make it equal to 0. If we cannot think of any combination of C sub 1, C sub 2, and C sub 3 to make it 0, then that makes it linearly independent. So let's have our second example. So we have 1 plus x as our first solution. We have C1, 1 plus x. And then the other one is plus C sub 2. So multiplied it with x. And then plus C sub 3 multiplied with x squared. And that would be equal to, or that would just be it. That's a combination. So we need to find for the values of C sub 1, C sub 2, C sub 3. So to make this one equal to 0. So the thing here is we can think for the C sub 3 as x squared. But then, so for x squared, as you can see on the given functions, x squared does not have any pair another x squared. Okay, so that's why the only way on how to eliminate that one Okay, so to make that 0, so C3 should be equal to 0. Okay, so to make that one, to eliminate the x squared there, so C3 should be 0. So thus, we don't have the x squared anymore. Then for x, I'm going to eliminate the x. So I have C1, so which is multiplied with the x here, and C2, which is multiplied with the x here. So that makes it C1. So possible, we could have C2 to be equal to 1. So if that is 1, so I should have a negative 1 for C1. So C2 should be 1, and then C1 should be negative 1. But then, I could have a negative C1 plus C2, which makes it 0. But the problem there is we still have C1 times 1. Okay, so we still have these. So C1 times 1. So therefore, the combination there is not totally equal to 0. So, what else? So probably I could make C2. If I'm going to make C2 is equals to 0, okay, so I eliminate the C2 times x here. Okay, so 0 times x is 0. But then, it's not possible to make C1 equals to 0 as well, because that's a violation. There are 3 zeros. Okay, so it's not possible to have 3 zeros or all zeros. Okay, so for the arbitrary constant. So in short, actually there's no combination for the values of the arbitrary constant so that would make this one equal to 0. Okay, so we cannot think, or there will be no values for the arbitrary, a combination of values for the arbitrary constant that will make the linear combination to be equal to 0. Okay, so therefore this is not equal to 0. So since this is not equal to 0, therefore this one is linearly independent. So since the three are linearly independent, then it would be possible that the three functions can be a solution of the differential equation. Okay, so since the three functions are linearly independent with each other. Okay, so that's how we do it. For example number 3, so this time so we have a trigo function. So we have cosine 2x, 1, and then we have cosine squared x. So the linear combination of the three, so would be C1, so cosine 2x, plus C2, so times 1, it's still C2, okay, or C2 times 1, and then plus C3 cosine squared x. So we have cosine 2x plus C2 times 1 plus C3 cosine squared x. So we have C1, C2, and C3. So can we make this one equal to 0? Recall, okay, so in trigo, so we have the identity for cosine 2x. Okay, so cosine 2x is the same as cosine squared x minus 1, right? Cosine, is this correct? Cosine 2x is equivalent to cosine squared x minus 1. So for the identity, cosine squared is 1 plus over 2. Okay, so I forgot. There should be 2 there. So cosine 2x is equals to 2 cosine squared x minus 1. So that would be plus 1 plus cosine 2x all over 2. Okay. So since we already have an idea about this, so I can make probably cosine squared. So I have 2 there, so I could make C3 to be equal to 2. And then I want a negative 1. Okay, so I want a negative 1 for C2. So I'll multiply it with negative 1. And then, so since that will make it equal to positive cosine 2x, so I should have a negative 1. Okay, so for C1, so to have a negative cosine 2x. So once I substituted this, so this would become negative 1. So negative C1 is negative 1, so negative cosine 2x. And then C2 is negative as well, so that would make it negative 1. And then plus C3, so that would be plus 2 cosine squared x. So this is the same as negative cosine 2x. So interchange the 2. So 2 cosine squared x minus 1, that is the same as plus cosine 2x. Thus making it equal to 0. Negative cosine 2x plus cosine 2x is equals to 0. Then therefore that makes it as linearly dependent. Okay, so those three functions are linearly dependent with each other. So thus, those are, again, could no longer be or could not be a solution of a higher order differential equation. Okay, so that is on how to check. Okay, so whether a given set of functions are linearly dependent or independent with each other. The downside here is we just need to think. Okay, so there's no specific method or formula that we're going to use, but rather, so we just need to think of the values of arbitrary constants to make it equal to 0. If it is equal to 0, then that makes it linearly dependent. If it's not equal to 0, then that makes it linearly independent with each other. Okay, so next is we have the Wronskian. So Wronskian can be used as well, so in determining the linear dependence or independence of a set of functions. The good thing with this, it's a bit longer solution as compared to the first three examples that we had. But then, so this one uses a mathematical approach. Okay, so to check so whether a given equation is dependent or linearly dependent, or whether the given set of functions are linearly dependent or independent with each other. So in Wronskian, so we're using the determinants. Okay, so we're using the principle of determinants. So in determining the dependence or independence of sets of functions. So let's say, for example, we have three solutions, or the solutions of an nth order differential equation. So that would be, so we start with f1, then f sub 2 up to f sub n. So that would be the nth solution of the differential equation. So in forming the matrix, okay, to find the determinant, okay, so of the solution, so we need to form a square matrix. So that means, for example, if I would have two solutions, then I should have two columns and two rows, okay, or a 2 by 2 matrix. If I do have a third order differential equation, so it should be a 3 by 3 matrix. So how do we form? Okay, so the first row will always be the solution of the equation. Okay, so the solutions of the equation. And then the second row, or the functions, sets of functions. The second row would correspond to the first derivative. The third row would correspond to the third derivative. Okay, so if the second order if it is a second order equation, so there would be two solutions. So since that would just be a 2 by 2 matrix, so we only limit our second row to be the first derivative. Okay, so to have a 2 by 2. Okay, so for 3 by 3, so I need to derive it further. So finding the second derivative, so to form a 3 by 3 matrix. And then so once we form that one, so we just use the determinant. Okay, so we find the determinant. Okay, so we find the determinant, or what we are referring as the Wronskian. Okay. So for linearly independent solution, if the Wronskian, okay, of the given functions is not equal to 0, then that makes it linearly independent. So it's the same thing as what we did for arbitrary constant. If it all equal to 0, that makes it linearly dependent. If it's not equal to 0, independent. So it's the same thing with Wronskian. If the Wronskian W is equals to 0, that is linearly dependent. Okay, so if W is equals to 0, that would make it linearly dependent. But if W is not equal to 0, so if this equals to 0, if it's not equals to 0, that makes it linearly independent. So this one is a solution of differential equation. This is not a solution of differential equation. So solutions of differential equations are linearly independent with each other. So for our fourth example, actually even after the last example, so it's the same as the first three examples. So this time around, I'm just going to use the Wronskian method instead of the arbitrary constant. Okay, so instead of the arbitrary constant, so I'm going to use a Wronskian method. So in Wronskian method, we're not going to get the linear combination of the three solutions. So rather, we're going to treat them independently. So that is, so we need to form the determinant. So that one can be made by, so W, so would be equal to, okay, so we're just going to write down for the first row the three sets of functions, or the three functions. So we have the first one, which is x, the second is x squared, and the last one is 4x minus 3x squared. So x squared, 4x minus 3x squared. So we so since this is there are three sets, or there are three functions involved, so we need three rows as well. So to form the second row, so we find the first derivative of x, so which is 1, and then the third row would be derivative of 1, which is 0. So x squared, the first derivative is 2x, the second derivative is 2. So this one, first derivative is 4 minus 6x, and then so we have derivative of this is negative 6. So in finding the determinant, we can do the product, okay, of the diagonals. Okay. So that is the downward, okay, so minus the upward. Okay, so the sum of the product of the downward terms, okay, so diagonally, okay, so can be found, so to form the Wronskian. So to find that one, so we need to copy the first two columns. So in this case, I'm going to copy the first two columns here, and then I'm going to extend it here, and then So this is what would happen. So we're going to get the sum of the product of this. Okay, so this would be the first term. So multiplied or plus the product of these terms, and then plus the product of this term. So that is, so we can write that one as W is equals to, so downward that would be X times 2X times negative 6X. So that makes it, so 6, 2X, negative 6, so negative 12X squared. So for the second one, so I'll have X squared, and then 4 minus 6X, and then times 0. So X squared, as long as there's a 0 there, that is already plus 0. Okay. And then lastly, so I have 1 times 2 times this one. So 4x negative 3x squared times 1 times 2. So that makes it, so 1 times 2 is 2. So 2 times 4x, that would be plus 8x. And then minus, so 2 times 3, that would be 6x squared. Okay, so the determinant can be evaluated, okay, so by the downward diagonal minus the summation of the upper diagonal. So minus the upper diagonal. So upper diagonal, so I'll start it with here. Okay. Then this is the second. Then this is the third. So as long as you can see already a 0, okay, so for that diagonal, then that makes it a 0 already. Then I have 2, negative 4x, and x. So 2 times x is 2x times 4. That would be plus 8x. So 2x times negative 6. So that would be negative 12x squared. And lastly, we have negative 6 times 1 times x squared is negative 6x squared. So what we can see here now, so W will be equal to, so negative 12x squared minus negative 12, that would be 0. 8x minus 8x is 0. Negative 6x squared minus negative 6x squared is 0 as well. So therefore, the Wronskian is equals to 0. And since this is equal to 0, then that makes it linearly dependent. So that is for our example number 4. So W, or the Wronskian, is equals to 0. So this is the same as with our first example. Okay, so it's linearly dependent. So we're able to think of the arbitrary combination of arbitrary constant that would make it equal to 0. But in Wronskian, so once we find the determinant of the matrix, okay, so using the Wronskian method, it would still be equal to 0. That makes it linearly dependent with each other. So let's have our second example. Okay, so this is the same as the second example. So second example, so we concluded that that is linearly independent. So therefore, for Wronskian, we're expecting that our answer here should not be equal to 0. Okay, so this should not be equal to 0. So form it. So W then, so I'll start with 1 plus x as the first solution, or the second function is x, and then the third function is x squared. So 1 plus x, so first derivative would be 1, then 1 is 0. So x is 1, and this is 0. X squared is 2x, 2x is 2. And then we copy the first two terms. And then, so downward, 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 minus the upward, upward, upward. Okay, so now W then will be equal to, So 1 plus x times 1 times to the first yellow diagonal. So that would make it 2 plus 2x. So 2 times 1 is 2 times 1 plus x is 2x plus, or 2 plus 2x. Then for the second yellow, we already have a 0 there. So x times 2x times 0, that makes it 0 already. And then for the last diagonal, x squared times 1 times 0, that would still be 0. Then minus, so for the upper pink diagonal, so it started with 0, that makes it 0 already. For the second, it's 0 as well. And then for the third, that would be 2 times 1 times x, that is 2x. So w then, so will be, so we have, okay, so 2x minus 2x is 0. But then, we have 2. Okay, so since w is equals to 2 and w is not equal to 0, then that makes it linearly independent. Okay, so we have the same conclusion. Okay, so just like on our fourth example or second example. And of course, for the last one, for example number 3, we had concluded that that is linearly dependent. So therefore, we're expecting that our answer here should be equal to 0 as well. So let's try to have as w. So we have our first function as cosine 2x, second is 1, the third is cosine squared x. So cosine 2x, the first derivative of cosine, it's negative sine 2x, derivative of 2x, it's 2. So derivative of cosine is negative sine. Then the second derivative, so derivative of sine is cosine 2x. So 2 times 2, that would make it 4. And this is 0, this is 0. Cosine squared x, so using chain rule, so I'll start with 2, then cosine x, then derivative of cosine x, it's negative sine x. So cosine squared x, so I'll start with the power, so it would become 2 cosine x. So cosine, and then derivative of cosine is sine. So that's, I'll have a negative 2 cosine x sine x. But then recall that this is the same as, this is a double angle. Okay, so 2 sine x cosine x, that's the same as negative sine 2x. Okay, so using identity, that's the same as negative sine 2x. And then that's the one that we're going to derive. So the derivative of negative sine 2x then, so will be sine is cosine. So negative cosine 2x, derivative of 2x, it's 2. So negative 2 cosine 2x. So let me rewrite this one. Or I'll copy this. And then, so we can rewrite that this would be cosine squared x, then negative sine 2x, and we have negative 2 cosine 2x. And then we copy the first two columns. And then, so we write our diagonals. So downward, so downward, downward. So upward, upward, upward. So for our W, so I'll have, okay, so as long as I can see, the first yellow diagonal contains 0. The second diagonal, okay, so that doesn't have 1. So 1 times negative sine 2x and negative 4 cosine 2x. So that would make it positive 4 sine 2x cosine 2x. Then the last diagonal would be 0. So for the pink diagonal, so I'll have, so minus, so negative 4 cosine 2x, so we'll have 0, so that would be 0. Second contains 0 as well. And then for the thirds, I'll have negative 2 and negative 2, that would be positive 4 sine 2x cosine 2x. And we can see here that that will cancel out. 4 minus 4, that would make it equal to 0. And thus, W is equal to 0. So therefore, that makes it linearly dependent. And that's it. Okay. So in summary, so again, so as long as the order is order 2 and above, then that is considered as higher order differential equations. There are two types of higher order differential equation, the homogeneous and non-homogeneous. As long as it involves a dependent variable y, so together with its derivative, then that is considered as homogeneous equation. But if the derivative and the dependent variable and its derivative together with a function of x is included on the equation, then that makes it as a non-homogeneous equation. And then recall that the solutions of the differential equation or higher order differential equations are linearly independent with each other. Okay, so linearly independent with each other. So once we think, okay, of the linear combination of the solutions or possible solutions of a differential equation, and then there's a combination of arbitrary constant that will make the linear combination equal to 0, then that makes it linearly dependent. So if the Wronskian is equal to 0, that makes it linearly dependent as well. So which is not a solution of a differential equation. But if the combination of the arbitrary constant, so there is a combination of arbitrary constant that would make the linear combination not equal to 0, or the Wronskian is not equal to 0, then that makes it linearly independent with each other. And solutions which are linearly independent with each other are a possible solution of a differential equation. And that is all about the introduction for higher order differential equation. So for next video presentation, we will be covering solutions of homogeneous equation with constant coefficient. So that is all from me. I hope that you've learned something, and God bless always.